So, hello everybody. So, let's decrease the sound a little bit. So basically today in this video, we are going to prove the binomial expansion. And right now I'm listening to a song right now, which is why I might vibe between different in the middle of nowhere. So please forgive me if I do that. So let's start. Not here. Let's go to third workspace, I guess. Let's start my paint. So just delete that. I need this. I do not need this. Okay, delete later. So I do not have really good experience with my paint, but I did learn a little bit just before making the video. So let's turn off the bar and let's select the color a little bit. This one's quite pretty nice. And where is that? Okay, this one. So hello. So today we are going to prove the binomial expansion. And let's just let it go. So I'm writing with my mouse, so it's probably going to be quite is there a shortcut for that? I probably do not know. I do not know any shortcuts of this program, so it's probably gonna be really bad. So today, as I told you guys, I'm going to be trying to prove the binomial expansion in my own way. I mean, not trying to prove. Here I go. So in the binomial expansion, this theory, I guess it's theorem anyway, this says a plus b raised to the power of n must be equal to this sum of from I starts from 0 to and goes to n, and combination of n comma I, a raised to the power of n minus I, and let's just move this a little bit, and times b raised to I. So this is basically the binomial expansion theorem, I guess. So we're trying to prove why this is why this is true. So let's start the proof. It's already been 3 minutes and I've not even got into the video. So so let's start. So first we're going to take some examples, because examples are quite necessary for anything. And in this video I'm just trying to teach you guys how it would be possible. So let's try a plus b whole squared. So we're going to do it the way we normally used to do it. A plus b whole squared is equal to a plus b times a plus b. This is what we learned in our algebra class. And due to some, I guess this is called distributive property, I do not know, sorry, but this is what we can basically do. I do not know the name of the properties, but this is true. So plus b times a plus b. And what we did in our algebra classes is we basically multiplied them with another property of algebra, and I do not know the name of the property, but if you plus b squared, and then we concluded that this is a squared plus 2 times ab plus b squared. So this is how we did in our algebra class, and we basically proved this. But we want this to be generalized, basically. So first, before that, we probably need to know what this c n comma I actually is. So for that, let's go somewhere around here. Okay, let's zoom in a little bit. So where is that? Well, this is right here, so it basically needs to be somewhere around here. Okay, so now we need to know what in the formula we saw last time. There's something called c n comma I. So we need to know what this is. This is defined as n factorial over n minus I factorial times I factorial. And what this means is, what this basically means, now we read this as combination of n comma I. This is how I read. I do not know what they teach you in your schools, but now what this basically means, now we need to know what combination is. So for what combination is, like, let's say we have 20 people, and there needs to, okay, let's go full anime style, right? Okay, there are 200 people in a school, let's say 2000, or else it's not going to be anime plot. So, and there needs to be a student council, right? And in the student council, only 5 people can be, 5 people can go into, 5 of the students can be in the student council. Let's just call S.C to student council. So the and in how many ways can we make the group of 5 people? This is given by this will be given by combination of 200 comma what is that, comma 5, and so your probability of if this was fully random, all right, if this was fully random, then your probability of getting into the student council and being the main character of the anime plot would be probability, let's call it P. This would be 1 over C combination of 200 comma 5. So yeah, now we can put the value, you can substitute this thing, and this would basically be 1 over, this is 200 factorial, and over, now 200 minus 5 is 195 factorial, times 5 factorial, and which would basically be, and it gets flipped over, right? When it gets flipped over because it's reciprocal. So this would be 195. Let's go quite big. So this would be 195 factorial times 5 factorial over 200 factorial. This would be your probability of, you know, being getting into the student council of 5 group if there were 300 people in your, 2000 people in our school. I'm very, very sorry here. We can always change this. I'm sorry. Let's just say, what is this? Oh shit. So where is that? Where was that? Where did I say that there are 200 people? I'm sorry. There are not 2,000 people in the school. I'm very sorry. Let's there are only 2. Wait, here I go. Why is it right there? There aren't that many people. There are only 200 people. I'm sorry, terribly sorry. Why is this thing not writing right now? Okay, I'm quite bad at these things. So there are 300 people in the school, and this would be that. Now now we have basic understanding of what combination is. Now we can basically learn what now we can basically see the logic of how the multiplication of the a plus b, that thing works. So what we basically do is, now it's kind of it basically looks like a Japanese kanji for some reason, but how did we do a plus b? Now we can have two sets. Now I'm just gonna represent them in a table, and what we basically did is a and b, and let's change the color for now. Let's make it kind of it needs to be kind of pink. So for a, so first a is going to multiply to b, and then a is going to multiply a itself, and then let's change the color again. Let's go full black here, and then b is going to go multiply with a, then it's going to multiply with b, and what we're basically going to happen, let's get to the normal color that we had back then. So this basically means that we have this set of the ordered pairs. I guess it's called Cartesian product of these numbers. So we have set of ordered pairs a comma a and a comma b, and let's see comma a comma c, I guess. Let's go full screen, I'm sorry. A comma c, oh, not b, it's b comma a time, and it's going to be b comma b, and the set is finite and a closed set. So these are the things, and what we're basically doing is what we did to get the actual value of a plus b raised to the squared is we can basically rewrite this as getting this set and multiplying everything in the ordered pair. Now let's just define a set define a set, let's call it set M. Now let's define a set N where everything in the ordered pairs, inside the ordered pairs, are multiplied. So set of N and everything is multiplied. So in this set we would basically have a squared and another ab, and in this set and we would have ba, but ba is equal to ab because ab equals ba, which is a property that we know. And then I'm writing with a mouse, so the handwriting is really bad, so I'm trying to speak as much as I can so that you guys can understand what I'm doing. And then there's going to be b squared. So these are the elements of this set. So let's define a operator. I'm just going to define it whatever I want to. So let's call it let's call it this. Anyway, let's define an operator. Let's define a function f of x. So what it does is if a set is given to the function, then it just adds every element of the set together. So let's say this, every element of the set and gets added. Oh shit, what did I do? Okay, every element of the set added. So if we give n to that function, so every element of the set should be added, and then it's going to be a squared plus ab plus ba plus b squared, and here you see we have ab. We basically have two ways. These two are same things because these two are basically the same things. We can add them up and we get a squared plus 2ab plus b squared. And now we can do the same. Now what we're going to do is we're going to do it, make it a bit general here. Every definition that I wanted to, everything that I wanted to define is now done. Where is that? Let's just break out of this because I'm kind of getting out of my hand right now. So every definition that we wanted to do is properly done now. Now we can basically say is in here. Let's just write something. Okay, this one. So every definition that we wanted is done. Now what we're going to do is we're going to try to do a plus b raised to the 3 raised to the power of 3. We're going to take this as an example to learn what's actually going on, and finally after that we are going to deep dive into this and then prove that. Right now it's just basic things, so something that everybody basically knows. So this is we already found out that a plus b squared times a plus b, we already know this. And we previously proved that a plus b whole squared is a squared plus ab plus ba plus b squared, and we basically have to multiply that with what's going on? It started to freeze a little bit, times a plus b, and we can say that in here that this must be equal to a times a squared plus ab plus ba plus b squared. Now why am I not just writing 2 times a plus b is so that when we are so that we can basically know what's going on in here. A squared plus ab plus ba plus b squared. Now why am I doing this? I'm telling you again, I want the coefficients of everything right here to be 1, because we basically do not know what the coefficient is, and this is why we just want the coefficient to be 1. Everything, coefficient of every, I don't know what do you call that, everything to be 1. So this is going to be a raised to the power of 3 plus a raised to 2 b plus b a raised to 2 plus b, which is plus this is b raised to 2 a, and this is again we have the second one. Let's take a look at second one. So this is going to be b a raised to 2 plus a b raised to 2 plus b raised to 2 a plus this is b raised to 2 a plus b raised to 3. So this is how we, and now I did this so that we can understand about what's going on a bit more. Now after this is done, now let's get into the real proof. Let's see how much video was. Okay, this is in 8. Okay, it's already been 18 minutes, and we haven't got into the real proof. These are all examples, so that everyone who's watching the video is on the same line, same point, or something like. Okay, now let's get to the proof. So in the proof, now we're going to a plus b raised to the n. Now we're going to make it a bit more abstract, and we're going to, according to the definitions and things that we told earlier, we're going to say we can say that a plus b raised to n is basically we can reimagine this as like there are n boxes, like there are n boxes. There can be any number of boxes, and in n boxes we have a b, a b, a b, and in these n boxes, first a multiplies to a, then it multiplies to a again, and this could go anywhere, right? This could go anywhere, and then a could multiply to b, and then b could multiply to a, or that b could multiply to b, or that A that we multiplied earlier could multiply to B, and B or we could say first B could multiply to A, B could multiply to B, and you know, basically every combination of every way that this arrow can go. Let's make it, let's change the color a little bit. Let's make it green, because I like green, not green, this blue. This is my favorite color. So it could basically go from here, it could basically take this way, or this could take this way, or this could take this way, or any way possible. And you know, if you have studied combination and permutation properly, we know that there will be it'll have two ways. You know, it'll have two ways, then two ways, then two ways, then two ways, just like that. The total number of ways that this line would be able to go would be 2 to the n, because there are n boxes in here, and each boxes gives it two possibilities. Now, but let's see, but because this is this, now if we take a look at this carefully, you see this is the sum of all coefficients of a plus b to the n. So if we have a plus b to the n, and if we add all coefficients together, we'll get 2 to the n. The proof will not be in this video, I'm very sorry, but this just literally says that we're in the right way. Now we can again you know, think of something else. Let's change the color to the normal color that we were doing. Now then, with this idea that we have said, we could say that okay, let's not do this here. Let's go somewhere far away, like oh, not this. I want to do this. Okay, anyway, doesn't matter. Where am I? Okay, let's go somewhere far away. So what we could think of this is this is quite not as good. Okay, this is what our previous colors were, and what we could think of this is that I wonder what this kanji means. I mean, like there are n boxes, right? N tables, and it goes on up to n, and they're like A, then we have B, A, then B, A, then B, A, then B. So we could say that as we, you know, talked about it earlier, the locus that we thought of could go anywhere in any way, because that is how we normally multiply. So according to the definition, now how can we represent a way in which that thing went, the line went? So we could say that this is some sort of array, and we could say that like there are n terms, okay, where there are n you know, boxes inside this array. So first it selected A, then it selected A, then it selected B, then it selected B, then it selected A again, and then B, things like that. We could represent everything in an array, and or else, I mean, according to the set we defined, there in the set where this goes everywhere, right? It goes everywhere at once, everywhere possibly, everywhere logically possible. It could go everywhere, and there would be those ordered pairs of, not ordered pairs, but ordered arrays of n numbers. Okay, there would be ordered arrays of n numbers, and those n numbers, and as we saw here, there were 2 to the n possible ways where the line can go. So there would be those ordered numbers, let's just define them. Let's just call them properly. Let's just give them proper names. So there would be like, let's say ordered pair 1, and not pair, that the ordered array 1 and ordered array 2, ordered array 3, up until ordered pair 2 to the n. Like, that's what we would have. And what we basically do is, now according to the definition, that something that we defined earlier, so what we can do is we can multiply everything in this array together. I'm basically going to make a shorter version of this video so that everybody can understand. I mean, it's not boring for normal people. And we multiply everything in here, and we add everything up. Now, what we know is that in this array, in this array of n elements, now if we consider this, right, there's this array where everything is filled with a. Everything is filled with a's, right? Basically, everything is filled with a, and there are like same number of b's. Now we have b's in here. A lot of b's, and those b's want to replace a. Now let's say 2 b's will replace a. Now, in how many ways can these 2 b's from this array replace 2 a's? This would be combination of there are like out of n b's, in how many ways can 2 b's be selected so that they can replace that thing, those a's. So there, out of n b's, we have to select 2 b's, and that is the number of arrays that will be made, where that would be number of arrays that would be made where there are 2 b's and n minus 2 a's. So now what will we get when we multiply everything in the array? When we multiply everything in the array, we will get, what did I do? Okay, what would we get if we multiplied everything? If we multiplied that everything in the array with everything, if we multiplied everything in the array, and if we multiplied everything in the array that we defined earlier, I'm having a hard time explaining this in words. There would be, as there are n minus 2 a's, this would be n minus 8 raised to the power n minus 2. And there would be 2 b's times b raised to the power of 2. This would be the multiplication of every element. And if we added everything up, let's take it from here. Let's not go further right now. And if we did something, for example, if we said there would be those things, and according to this thing that we defined earlier, where are all those? Oh yeah, it's up here. So it's a big long board, and in here we have seen that in this example, not actually this example, probably, where are those things? Okay, I would not expect anybody to be really anyway. So in this example, I guess we said that there could be it would rather go not selecting any B. It could select one B, or it could select two B's, or it could select three B's, or it could select four B's, up to it could select or no B's, or it could select n B's, right? This is how we said those things worked. So we said, okay, I guess it happened when I messed things up back then. Okay, this thing's freezing real bad. Let's just start a new document then. I'm kind of feeling too bad for this one. Let's quit that off. And let's okay, it's my paint, right? Okay, great. Now it's really more good right now. So then we could have select 0 B's, or it could select 1 B, or it could select 2 B, it could select 3 B, and it goes up to n B's. So and there would be and when we add, and there will be a combination of n comma 1 ways to select 1 B, and there'll be combination of n comma 0 ways to select 0 B. There'll be combination of n comma 3 ways to select 3 B's, and just like that, when we add everything up, when we multiply everything up, there would be combination, multiply everything up and add everything up, there would be the coefficient of anything raised to anything with a to the power of n minus I, b to the power of I would be combination of n comma I. This would be the coefficient of everything. This would be the coefficient. C n comma I would be coefficient of every element with everything in the expansion with the power of a to the n, where a to the n minus I would be power and b to the I. You get the point, right? And we basically know that it goes from with that abstraction that we showed earlier, we know that that I could go from 0 all the way to n. So, and as we add everything up, I would start from 0 to n, and we always add n n comma I. This would be the coefficient, and the power would be, the other thing would be a to the I, n minus I, and b to the I, which basically proves, which would be equal to, now we know that, which must be equal to a plus b raised to the power of n. And here we have proven the binomial expansion, and the video is basically 30 minutes long. Too bad, but anyway, at least we have proven the damn thing. Now, as we have proven the damn thing, nobody is going to watch this 30 minutes video. So I'm going to make a summary video so that I can show my proof to people. And if they say I do not understand or something, I'll just tell them to watch this 30 minutes video. Right? Great. And if you like this video, then I suppose I don't expect you to like this long video, but please comment. I don't want any subs. I just want some comments. I just want to know what you guys feel, what you guys actually feel about my proof. Just comment. Please. That's it. Thank you very much. This was the proof for binomial expansion, which is kind of stupid, but anyway, I have an hour-long video where I basically try to fix bugs in a program, so this is not the worst video, I guess. Thank you very much.